Yes,
Okay.
sir. Yeah.
So those who joined late, I was telling them that today I'm not feeling that great. I have some severe headache. I'll try my level best to finish whatever I can. But in case if I can't, we will have a, so anyway, to compensate for the last class, we will have a class on Monday for maybe 1.5 hours. Okay, is that fine? Monday is a holiday,
Okay,
but
sir.
we can have the class. How was the quiz, by the way? Okay, everyone.
Yes, sir.
We're able to. Okay. Okay. So in the last class, towards the end, we were discussing about um, uh, uh, um, the behavior, the long-term behavior of a Markov chain, right? For example, this is what I was talking about. For example, we have seen this Kolmogorov-Chapman equation, right? So what does it say? It says if you look at the probability transition, for example, P after n step, right? That means this is a vector which essentially says that you start. Okay, so let me write it like this. Um, um, if I want to go from I to j in n steps, how do I write this? You can recursively write this as what? Hmm?
So I to some kth step, and from
Okay, so
kth step.
let me write it like this. So if you take P is the probability transition matrix. If I take P power n, what is the ijth element of this corresponds to? Is the probability of going to
J
j
from I in steps.
starting from I in n
In
steps,
steps.
right? So clearly, if I ask this question of what is the probability that I go to a certain state after n step, right? This might change over time. Meaning, if you increase n, the probabilities might change, right? For example, suppose I start at state I, okay, and I start at state I, and the probability that I go to state j in n step is this. This I can alternatively write it as follows, right? So what does this corresponds to? You have this matrix, and there is the ijth entry here, right? This is the ijth entry, and I want to pick that ijth entry. So how do you pick that ijth entry? Hmm? One way is, of course, let's look at this, right? So you have 0, 0, etc., 1 and 0, etc., 0. Okay, this is the ith um, or jth. Okay, is it jth or ith? So essentially, when you multiply, I should be able to get this particular thing. So if I do this, what do I get? I get a vector, right? What will that vector be? So essentially, it will pick all the what? Ith row, right? What is ith row? pi1, pi2, etc., pin, right? If this is, for example, power n, so this will be in n steps, right? Do you agree?
Yes, sir. Yeah.
Right? So that means if I want to compute the probability that I start at I and go to some state, right? This is state I, and I go to some state, right? The way to obtain that is you start the Markov chain as state I. Sorry, this is not J. This is ith position, and run the Markov chain and let it evolve and see what is the probability or the chances that you will end up in state, let's say 1. You repeat the process and count the number of times you end up in 1 divided by the total number will give me the probabilities, right? This is what it is. Now clearly this is dependent n on n, right? So what does this corresponds to? This is, you can think of this as the probability with which I'm going to start in state some k, right? In fact, the probability that I start in state 1 is 0, state 2 is 0. In fact, I start in state I with probability 1. That's a certainty, right? So this is what it is. Now, suppose this is the case, okay? Suppose there exists a pi vector, of course, such that pi p equal to pi, where this pi, if you sum, this is pi is a vector, if you sum over all pi, it will be 1. That means it's a probability vector, okay? And pi I is greater than or equal to 0 for all I. Okay, suppose this is the case, right? So now the way you can interpret pi p, what is the interpretation of pi p? Can somebody tell me? Pi is a vector which corresponds to a probability, right? Because so for example, the first entry is the probability with which you will pick state 1. Second entry will be the probability with which you will pick state 2, and so on. So what will be pi p?
Combinations of rows of p.
That is true, but what does this represent? So what does this represent? So for example, if n equal to 1 here in this case, right? So this is again, this is some pi wherein the probability that I pick state I is 1. That means I'm going to start the Markov chain with state I. So if I take this as my pi p would give you what?
Joint probability.
No, it gives
Total
you the probability.
probability.
No, it gives you the probability with which you go to some state starting from I, right? So for example, pi1, if n equal to 1, pi1 is the probability with which. So okay, so if this is p, right? What does this corresponds to? This corresponds to pi1, pi2, and so on, pin, right? This gives you the ith row of the P matrix. So what does this corresponds to? This is the probability that you start at state I and go to state 1 in one step, right? The immediate transition. Pi2 is nothing but probability that I start in state I and go to state 2 in one step, and so on, right? This is what I get. Do you agree? Is that fine?
Yes, sir.
Okay, everyone, or should I explain this?
Samoti totally 0, right? I mean, I cannot go I to another state in one step.
I can go, right? I can, in fact, depending on the Markov chain, I can go.
Okay.
Right?
Okay.
Yeah. Sumit, is that clear
Yes,
or
sir.
no?
Yes, sir,
Praveen,
Yes, sir.
Ayush, and Jayant?
Yes, sir.
Okay, fine.
Yes, sir.
So now this tells me, so now if you look at pi p, right? So this gives me a vector, right? Do you agree? So what does this result in? Can somebody tell me what does this result in? So this will tell me with what probability I'm going to start in each of these states. Now with that probability, so think of, okay, so I'll give you an example. Okay, maybe an example would help. So suppose I have two states, okay, 0, 1. This is P. This is 1 minus P. This is again P. Nice Markov chain. So if you look at the P matrix, how does that look like? Pij, right? 1 to, if you go from let's say 0 to 1, right? What is the probability? P. 0 to 0 is 1 minus P, right? And this is P, this is P, this is 1 minus P. This is the transition probability, right? So now what I'm going to do is I'm going to pick a pi. For example, I'll say pi. Well, pi is not a, maybe I'll use a different notation. So the vector pi is q, 1 minus q, times 1 minus p, p, 1 minus p. What will this give us? See, essentially what I'm doing is I'm taking a coin whose bias is q. The probability of head to occur is q. I'll toss. If it is a head, I'm going to start from state 0 and ask what is the probability that I go to state 1 or I remain in state 0, right? That is probability P and 1 minus P. On the other hand, if it ends up in tail, that happens with probability 1 minus Q, then the transition would be, I'll be in state 1 and I can ask what is the probability that I remain in state 1 or go to state 0, right? So this product gives you the average of that, right? What does this give us? This will be Q times 1 minus P plus 1 minus Q times P. This is the first element. The second one will be Q times P plus 1 minus Q times 1 minus P. Can you guys hear me? Hello?
Yes, sir. Yeah.
Hello? Okay. So Q times 1 minus P is what? Q is the probability with which you start in state 0, right? Q times 1 minus P is you start in state 0 and you remain in state 0, right? Plus 1 minus Q. What is 1 minus Q? The probability that you start in state 1, and P is the probability that you go to state 0, right? So essentially this, the first term essentially tells you what is the probability that I end up in state 0 after one step, right? This will tell me what? Q times P. Q is the probability with which I'm going to start at state 0 times P. That means I'm going to state 1, right? 1 minus Q is the probability with which I'm going to start in state 1 times 1 minus P. I'm going to remain there. So essentially this gives you the probability that I end up in state 1 after one step. That's what it gives us, right? So that means okay, so that means this probability, so this is nothing but, I can call it as, let's say, pi 0 and in one step, pi 1 in one step, right? This is what I get. Do you agree? Right? So now, if I take the same coin with bias Q and toss it and start in one of the states and run it for 2 times, what do I get? I get Q 1 minus Q times this probability, right? So 1 minus P whole squared plus P squared, 1 minus P times P plus P times, so what will happen to the other thing? So 1 minus P times P times 1 minus P is 2 times 1 minus P. So what will happen to the other one? It's P times 1 minus P and so on. So this will be 2 into 1 minus P times P. This will be 1 minus P whole squared plus P squared. So this corresponds to P squared matrix, right? So if I start with state 0 with probability Q and state 1 with probability 1 minus Q, the average after 2 steps, I'll end up in state 0 is phi 0. This product will give me that. Do you agree with this? I mean, is this calculation fine?
Yes, sir.
Everyone?
Yeah. Sir, this pi is always we
Okay.
are starting from the 0 only, sir. Like pi is a vector.
Which one?
So this pi that we
No,
are
pi
talking.
is a vector, right?
Yes,
So
sir.
for example,
Pi is a vector.
I can call this as my pi, right? So don't relate this pi to this equation, okay? This equation we haven't talked about that still, okay? So pi
Okay,
is some
sir.
vector. So it essentially says with what probability you are going to start in state 0 and what probability you are going to start in state 1. If you have n states, it gives you the probability with which you are going to start in each of those states, right? So when you multiply by P, it will give me the probability with which you will end up in state I after one step, right? If you start with probability pi, right? Probability vector pi. Is this fine?
Yes, sir.
So essentially what this says is, if I want to, if I ask this question, what is the probability with which I'll end up in state K after n step? So that depends on the step n, right? As n changes, you will get different probabilities for you to be in state K, right? So that is something that is variant, right? So if, for example, probability that you are in state K after n steps depend on n, then the chain is non-stationary, right? So, for example, after 10 steps, the probability that you are in state 0 is 0.3. After 20 steps, the probability that you are in state 0 is 0.2. It's changing over time. So, it's a non-stationary chain, right? Do you agree?
So non-homogeneous, no, sir?
Non-stationary. Well, no, it's homogeneous because I'm picking the same. So if you look at these transitions don't change over time. It's fixed. But over time, the probability of you being in some state will change because the way you started your Markov chain, right? For example, you pick state 0 with probability q and state 1 with probability 1 minus q. If that q happens to be such that the probability that you are in state k after n step depends on n, then it's a non-stationary Markov chain, right? How do I make it stationary, right? How do I make it stationary? So what do I mean by that? If I ask, what is the probability that you are in state k after n steps is independent of n, then we say that the Markov chain is stationary, right? It doesn't change over time. So I can just use one probability for on an average I'll be in some state which is not going to change even if you run the Markov chain 1000 steps, right? So how do I ensure that? For example, what is happening here? Pi 2 is basically this complicated beast times this, right? So suppose, now let's look at this. Suppose pi p equal to pi. Okay, pi is a probability vector. That means I'm going to start in some state with, so if I'm going to start in state I with probability pi I. So pi is a vector, okay, which is a probability vector. Okay, then I'm going to choose this probability vector in such a way that pi p equal to pi. Okay, if this happens, then so what does this pi gives us? This gives us the probability. So if you look at this product, it is the probability that you are in state. So first entry of pi will give me the probability that you are in state 1 after one step. Okay, the second entry will tell me the probability that you are in state 2 after one step, and so on. So how do I compute the probability that, so you start your state at pi, okay, after 2 steps it's pi squared. Do you agree? Pi squared pi will p squared pi will pi p squared will give you the probability that you are in some state I after two steps if you start your Markov chain with the probability vector pi. Is that clear? Yes or no? I can write it like this: pi p times pi p times p. What is pi p? It's pi.
It's
Pi
pi.
p. This is pi only. So the probability after 2 steps you being in any state is same as you being in after one state, right? Or one step. So that means in general, if you look at this, pi p power n is pi invariant, right? It's invariant with respect to n, so it does not change over time, right? So now it has its own benefit, right? Because if I start in the state pi, I'm done over after n step. I'll always, the probability of you being in some state will not change over time, right? Which is good. I have to compute one probability pi and I'm done, right? So the question now is under what condition? So there are 3 important questions that one can ask, right? So first question is, I said suppose, right? When this suppose happens, right? So under what condition pi equal to pi p is have probability vector solution, right? Right, this is the first question. And what condition will have this, right? Is there any condition? Okay, when is it unique? Okay, that's the second question. The third question that we can ask is, if you look at this p power n, right, the nth power of p, so under what condition each row p power n converges to a probability vector, to a probability vector pi such that pi equal to pi p. Well, so these are the three questions that we can ask, right? For the first two are quite natural, right? The first thing is, when do we have a probability solution, right? Probability vector solution. The second thing is, when is it unique, right? Otherwise, you'll have multiple initialization of Markov chain, which will result in a stationary behavior. So when is it unique? And the third question is, well, can we recover this by just taking the nth power, right? That's a very easy to compute thing, right? So now let's try to answer some of these. In
Hello,
the yes.
sir, let's assume pi into p is not equal to p, but this product pi into p is always result in some probability vector, right?
That is true, but what I'm saying is, I want pi equal to pi p, right? See, pi times p is always a probability vector. There is no doubt about it, right? But if you look at pi p squared, that's a probability vector, but pi p squared is different from pi p, right? That means each time as the Markov chain evolves, the probability of you being in some state will also change, right? That is something that I don't want to happen, right?
Yes, sir.
Okay, so let's look at it. Let's look at this chain, right? So for you, 0 means a bad channel, 1 means a good channel, okay, in your communication context. So if you start have, or I don't know, I should not say bad channel, good channel, because I don't have control over it. Maybe how do I put it? Okay, so let me say, let me denote 0. So if it is 0, then it's something bad, and 1 means something good, okay? Or 0 means something medium, 1 means something good, or something like that. Now, if I have, if I can start in any of these states, right? Now I'll toss a coin and start in one of these states and let the chain evolve, right? On the long term, right? So after n steps, if I ask what is the probability that you are being in bad state, if that's going to change with n, I have absolutely no idea, right? So the chain will act crazily, and I have no control over it. If that doesn't change, then I can see what happens in the long run very clearly, right? Is that fine? Yes or no?
Sir, the signal was very disturbing. We missed some of the words. I mean, I missed some of the words. Hello?
Okay. I was just saying, yeah. Can you hear me now?
Yes, sir.
Okay. So I was saying, if you think of 0 as bad state and 1 as good state, then if you toss a coin and start in one of these states and evolve, and if I ask what is the probability that you are in state 0 after 100 steps, and ask the same question after 200 steps, if these things are different, then it's very hard for me to see what is the long-term behavior, right? I mean, how things behave over time, it becomes difficult. Whereas if it is invariant, for example, it doesn't change over time, I just need two numbers to describe the whole thing, right? I just need what is the probability of you being in 0 state after any number of steps, you being in state 1 after any number of steps. That's all. I need two numbers. In fact, I need only one number in this case, right? That will describe the whole process. The only thing is I have to initialize my state or basically I have to choose my coin appropriately, right? Q and 1 minus Q should be such that Q1 minus Q times P should be equal to Q1 minus Q. That's all. Okay. So you can clearly see, right? So for example, in this example, right? So Q1 minus Q, 1 minus P, P, 1 minus P. Okay. So when do you think, okay, so let me make it very concrete. Okay. Let me not even say 1 minus P. So 1 minus P is 0.3, and this is 0.7. Okay. Is this fine? No, I don't want that. Just give 1 by 3, 2 by 3. Okay. Is this fine? So can you compute and tell me what is, I want this, basically I want this to be equal to Q1 minus Q. So this is easy, right? So Q by 3 plus 1 minus Q by 2 times this is equal to Q. The second one would be 2Q by 3 plus 1 minus Q by 3 is equal to 1 minus Q, right? So now I have to solve for this. So what will I get here? So if I solve for Q from these, I should be able to. So essentially, what is this saying? Yes, can somebody tell me what is this saying?
Sir, is it like eigenvector?
True, it's an eigenvector with eigenvalue being 1, and the eigenvector should be a probability vector, right? That's it's a problem in linear algebra now, right? So what can you say from this? See, Q by, so there are 2 equations and 1 unknown, right? Is that correct or no?
Yes, sir. Overly determined system.
So what can you say about this?
There may or may not exist a solution.
Okay, so let's see what this gives us, right? So this will be 2Q by 3. See, first one will basically cancel out, right? So what will happen? 2Q by 3 and 2 by 3. So 2Q by 3. And if you take it to the other side, it will be 2Q by 3. They cancel, and hey, there's something wrong, right? Did I write this correctly? 1 by 3, 1 by 3. Yeah, 1 by 3, 1 by 3, P, 1 minus P. That's correct. This is correct, right? So I2,
So
0
Q will
to
be
1,
half, I think.
0 to
Q will be
0 to
half.
Q will be half. So
Yeah.
half will give you a solution. So it's half, 1 by 6 plus 2 by 6. 2 by 6 plus 1 by 6. That's correct, right? So Q equal to half is one solution, right? Are there any other solution? See, what if we get 1 and 0 here? So this will be 1 by 3. No, this won't give me anything, right? It's not the right thing. So half and half, right? So this is the solution. So essentially I have to take an unbiased coin, toss it, and start from the state. So if you ask what is the probability that I'm in state 1 after 100,000 steps, what is the probability? Same thing, right? So half times 1 by 3 plus half times 2 by 3, which is 3 by 6, 1 by 2. So the probability that you are in half state 0 is half, and probability that you are in state 1 is half, irrespective of the number of states, the number of steps that you take, right? So, but then, well, this is a very specific case. So now we need to answer this question for a general.
This is like pi is a uniform distribution of their n step we take 1 by n.
Yes, it is. No, it's that may not be the case in all. So that may not be the solution in all the cases, right? I can construct a Markov chain where uniform distribution need not be, right? Well, will it be?
Sir, here what we are doing, we are modeling the scenarios for our own benefit, right?
Yeah, so we are asking a question which will benefit us, right? What kind of Markov chain will have pi equal to pi p as
Sir,
there exists a pi probability pi such that pi equal to pi p. That's the first question. The second question is, when is it unique, right?
but sir, does it not change the, or I mean, if there is any original problem, doesn't it change? I mean, for our own benefit, we are
No, we are
playing with the
asking this
variables
question.
and.
See, if I want to talk about long-term behavior, right? The first one will kind of says, well, there is a pi. So if you start there, then I know the long-term behavior. But the issue is there could be another pi, let's say pi dash, such that pi dash is equal to pi dash p. In that, if you start with pi dash, the behavior in the long term will be different from pi, right? Therefore, I need uniqueness. So under what condition this pi is unique? Then it kind of settles the scenario, right? Do you
Yes,
agree?
yes, sir.
Then I know the long-term behavior uniquely, right? It doesn't matter. There is only one way I can initialize so that in the long term, it remains the same, right? The third question is, how do I find it? I mean, one way is, you just take p power n and, well, it turns out that this is the case.
Sir,
Yes.
so it is like a Banach fixed point theorem, sir. Like we are looking for a fixed point. If we assume that P as an operator,
Huh?
then sir,
Yeah,
we are
I
just
can.
fine.
You
Is it a
are looking for a fixed point, but that fixed point is also not any fixed point, right? It should be a
yeah, that should be
probability
the
vector.
U.
Yeah.
Oh,
That's the constraint. That's the difference between, let's say, fixed points and these things. Fixed point is easy, right?
yes,
Fixed
sir. If
point.
suppose if we have an operator, then we always get, I think, sir, in a finite dimension. Like here, we
Yeah,
are working on a finite dimension, so we always have a fixed point. But that fixed
always,
point
right?
should be
Yes.
the probability vector, no, sir.
Probability vector. That's the issue. Is that fine?
Okay, sir. Yes, sir. Yeah.
Okay. Okay. So now let's try to answer this. Any questions? So I'll pause for a minute or half a minute. Any questions? And moreover, we are considering only finite Markov chain. Okay, so we can extend this to an infinite or countably infinite Markov chain, but I'm just talking about finite Markov chain here. The techniques are quite similar, but it goes into renewal theory and all that. Let's not. I think last time I did it, but this time I didn't talk about renewal theory, but I used those techniques. Okay. Any questions? No. Okay. So now let's look at the first result. So okay. So actually, this is a proof of something. So I don't want to write formal theorem and then prove it. Let's naturally see what is it that I get. So what is it that I want to understand? So basically, the first thing that we are going to prove is the fact that if you take p power n, so I can look at this, answer this question in any order, right? For example, if I answer third, right? Suppose I take p power n and show that it converges, and it converges to a probability vector pi, and then show that pi is equal to pi p. I'm done. Then finally, I should ask, when is it unique, right? Let's take that approach now. Okay. So now towards that, let's look at Pij power n plus 1. I mean, I start at I, go to j in n plus 1 step. Kolmogorov-Chapman says you start at I, go to an intermediate step, intermediate state k in one step, and from k you go to j in n step. So it's some more all k, right? Kolmogorov-Chapman. Do you agree?
Yes, sir.
Now I can start from k and go to j in n step, but if I start in different states k, I'll get different probabilities. I'll pick the best, meaning the maximum. Okay, then this would be an upper bound. Okay, I'll write that. What does that mean? Pik max overall L P Lj in n steps. Do you agree? Is this fine? So this is independent of k, right? So I can pull this out. So what do I get? I get max over all L P Lj n in n steps times summation over all k Pik. So I start at I, and I go the probability that I start at I and go to some state k. That's what it gives us, right? So this probability is equal to 1. Do you agree? So this will be,
Hello, sir.
yes.
So can you once again repeat this thing? This
Which one?
max, the summation PIK max.
So if I replace, for example, this guy here, if I replace this by maximum, right, I'll get an upper bound. Do you agree? See, this is from K to J, right? If you give me a particular K, I know the probability that I go from K to that J in n steps. But if I replace this by max, that's an upper bound, right? Do you
So,
agree?
but then there will be discontinuity, right? If I go to from I to K, and then max of that there will be discontinuity.
No. So it has got nothing to do with that, right? So I'm just replacing it by a larger quantity. That's all. And pulling that out. That's all I'm doing.
So, but my question is, K is a state, right?
K is a state, yes.
So if we are going from I to K, and then we have to go from K to J,
Correct.
right? But we are going from L to J.
See, the probability that I go from I to K is fixed Pik. And from K to J in n step is Pkj, right?
Yeah.
I'm going from K to some state J in n steps, right? That is Pkj. But what I'm doing, this is the number, right? This is the probability that I have to multiply in order to get the result. But instead, I'll multiply by some other K star, let's say, okay, K star to J. This probability is Pk star J in n step. So this probability is greater than that. So suppose when we compute this, instead of using Pkj of n, this probability, I'll use this probability. It will always be larger, right? It gives you an
This is
overestimate of the probability, right?
I mean, sir, you are just mathematically writing it.
Exactly. There is no,
Yeah.
mathematically writing it. That's all. Replacing Pkjn by something larger. That's all I'm doing. Is that fine?
Okay, so this is nothing to do with the state from where we are traveling, just a number.
Just a number. I'm going to replace. So instead of going from K to J in n step and looking at the probability, I'll look at that state K star, which gives you the largest probability, and replace that by the largest probability. So it gives you an upper bound, right? Okay. So now, is that fine? Okay. Yeah. So now, let's also do the same thing in the reverse direction, right? I can do that. So this gives you an upper bound. So let's look at Pij again, n plus 1 step. Okay. This is again overall state K, Pik, Pkj of in n step. So instead of replacing Pkj n by max, I'll replace it with min. So that I get a lower bound, right? Pik minimum overall L PLJ in n step. So this is nothing but minimum overall L PLJ of n. Well, I can write this and make sense provided this is greater than 0, right? So in fact, this should be, I want this to happen. Okay, the minimum PLJ, that means the probability that I start at a state L and go to some state J in n plus 1 in n step, that probability should be non-zero for every n. Otherwise, this will give you a trivial result. It says 0, right? Which doesn't make any sense at all. Do you agree? Is this fine?
Yes, sir. Every positive should be positive only. Otherwise, we are not accessible. These states
No,
are
this
not
is still a
accessible.
lower bound. It's a trivial lower bound. It says it's greater than or equal to 0. So it doesn't make any, right?
Yes, sir, it
It should
has
be
to be,
greater
sir,
than 0.
greater than 0. Yes, sir.
Okay, no, you cannot say that it has to be. We want this to be, right? Otherwise, this bound is trivial. It says is greater than or equal to 0. If this is 0, right? Okay. So now, what do we get? What did we get?
No, sir. Initially, sir, we have defined, no, sir, like a state J is accessible from I if and only if, sir, Pij is greater than 0 only. And here we are talking about the accessible states only. So it has to be positive for all.
No, right? So accessible, fine, but if it's transient, right? So eventually, as n becomes larger and larger, in the limit it can go to 0.
Okay, sir.
Hmm?
Okay, sir.
Okay, for every n, I want this to be greater than 0. That's all. Okay. So now, what does this give us? This gives us Pij of n plus 1 is less than or equal to max over all L Plj. So that means this is true for every I, right? You take any I, this is true. So that means if I take max, still that is true, right? Do you agree? Well, I'll take n plus 1. Do you agree with this? Well, I'll do a small change here just to, oh my God. Instead of I, I'll write it as L, okay, the index change. So what does this give us? This says the max, if you look at the maximum, L is the row, right? If you take a row and look at the maximum element in the row of a P of the P power n plus 1 matrix, right? That's always smaller than or equal to max on the same row of P power n matrix. So it's monotonically decreasing. Do you agree?
Yes.
So what is this saying? This says P I, well, same thing, right? I'll just use PLJ, minimum over all L is greater than or equal to PLJ of N. Okay, so that's what I get. Again, the minimum element in the Lth row is again monotonically increasing. You understand, right? The maximum is monotonically decreasing, the minimum is monotonically increasing. Okay, that's what it says. Is this fine, everyone? Okay, that's one of the lemmas in the book. Okay, so it says the rows of, if you look at this, if you look at a row, let's say this is your maximum element and this is your minimum element. The maximum element, this is n plus 1. So the maximum element is decreasing with n. Minimum element is increasing with n because it's greater than or equal to. So what do you expect? So max is here, min is here, and this is increasing, this is decreasing. So hope to converge somewhere, right? You are squeezing all the in between elements. So all these elements in between are squeezed between max and min, right? So that means it seems to converge, right? That's where we are heading towards. Is that fine?
Yes, sir, yeah.
Okay. Okay. Next, what is it that we have to do? So this is basically a theorem. Okay, so you can write it formally. Okay, this is what we have. Okay. Okay, so the next thing that we will do is the following. So if I were to prove that the max and the min, right, of the Lth, sorry, Lth, so the max and the min of a particular, sorry, did I say column? Row? No, it's actually column, right? You guys didn't alert me. See, I'm looking at J, right? So if you fix a J, this is the column that I'm looking at, and minimizing overall. Yeah, so this is the maximum and this is the minimum. That's it. This is the column, not the rows. Okay. Okay, now the next result that we are going to look at is the following. Suppose let's say I prove this. Okay, so max for all I, Pij of n plus 1. Okay. Well, this in the limit, okay, as n goes to infinity, ready, goes to something, okay, some star, and min overall I, Pij of n plus 1. This also goes to the same limit, right? What can you infer from that? What can you infer from that? Suppose this happens, let's say. What can you infer from that?
Sir,
Yes,
anything in between this will go to that only, sir.
yes. So max goes to a number, min also goes to a number. So I'm taking min and max over I, the rows, right? So basically, what is happening here? So ith row, right? So I'm sorry, I think I did two repeated mistakes, right? It should be a column or row.
So
It
this
should
should
be
be
a row,
column.
right? I was right before. It should be a row. Okay.
So why, sir? So we are changing the L.
So you fix J, right? What am I doing? So let's look at this P1, 1, 2, 1, 1, P1, 2, right? I'm taking so and P21, P22, right? So I'm fixing J. That is the first column, and then minimizing overall. Yeah, you are right. I'm sorry. I'm really sorry for this. It should be a row. Okay. So now, if the all that I'm saying is the max and min both goes to the same number as n becomes larger and larger, right? What does that amounts to? Essentially, if you look at a particular row, or a particular column, right, all the elements will be equal. Do you agree? P power n looks like this. Okay, for large n. Okay, this is very large. Looks something like this. This will be A1, 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 etc. A1 will be A2, A2, etc. A2, and so on. AN, AN, etc. AN. All the columns will be the same. Okay, that means all the row vectors will be the same. Okay, it will converge to the same row vector. Okay, so well, that row vector turns out to be pi. Okay. Now, one way of verifying whether this is true or not is as follows. So you look at the difference of these two, right? Max minus min, right? If I write that as some constant times something that is smaller than 1, and you do recursion, okay? Let's prove that and see what does that mean, okay? So let's start with this. So you take Pij n plus 1 is summation over all k Pi k Pkjn. Okay. Now I can do the following, right? So I can essentially, I'll do it in 2 steps. So I can just do k not equal to L min. Okay, I'll say what this L min is. Pik Pkj of n plus whenever k equal to L min, so I get Pi L min times P L min J of n star. Is this fine? I'm just splitting. I'm pulling out one. I'm writing one of the terms in the summation explicitly. That is the L min term, right? L min corresponds to the minimum. That's all. Okay. Now this bound is also straightforward. I'll replace Pik. I'll replace Pkj by max overall K or L PLJ of n. Okay. And then again, I'm going to replace this Pi L min, and I'm going to replace this with, well, PL min by definition is the index L that gives you the minimum PLJ n. Okay, so this will be same as, okay. So essentially, this and this are the same, okay, because I have chosen L min to be the minimum of this. So if you look at the solution of this, minimum overall L PLJN, that will give me L min. Okay, is that fine? Okay, the next step would be, I'll just separate it out. Okay, so I can pull this out. Okay, so what will happen? I'll have max overall L PLJ of n. This is what I have, times summation over all k not equal to L min Pik. So well, if I include, if the summation was summation over all k Pik, it would be 1, right? But which is the term missing? The only term that was missing is Pi L min, right? So what I will do is I'll add PL min and subtract PL min. Okay, so I'll write it in different color here, just for your Pi L min plus, sorry, minus PIL min. I can do that because max over all L PLJ. Are you guys there? I hope I haven't lost you guys.
Yes, sir.
Okay,
Yes, sir.
Yes,
you are
sir.
there.
Yeah.
So now if I add PIL min to this, I'll get this times 1, right? Then I have to subtract. Subtract what? PIL min. That is a subtraction term. And I have a max overall L PLJ of n. That's because this subtraction times this term will give me this. And I have to minus times minus plus, so I'll get this term. So this term is PIL min times minimum for all L PLJ n. Okay, is that fine, everyone?
Yes, sir. Yeah.
Okay. Okay, now okay, so let's make some assumptions, right? So let's assume this PIL min. Okay, so basically, okay, I'll do that. I'll write it. Define. Let's say alpha is minimum for all ij Pij. Okay, if I use alpha to be this, so what is it that I can write? The above. See, this alpha is minimum or all. Basically, I'm going to take the entire matrix P and look at the minimum value, right? So what does this give us? This gives us PIL min. That is, you are fixing the ith row and look considering the minimum here. But alpha is definitely less than or equal to PIL min. Do you agree with this? Solve that small.
Yes, sir. Yeah. Yes, sir.
So that means if I replace PIL min by alpha, this should be a upper bound, lower bound, because there is a minus times this. Do you agree with this? Fine.
Yes, sir. Yeah.
Okay. Now I get a lower bound. Now you can do the same argument. Repeat the argument with min max roles interchanged. We get what? We get an upper bound. We get a lower bound. Here it's a did we get a sorry, what did I do? Sorry, this is an upper bound, right? Because alpha is the least, I'm subtracting, I'm replacing minus of something larger by something smaller, so it's an upper bound, right? Yeah. So now this particular if you repeat the argument with the min max interchanged, I'll get Pij of n plus 1, same thing but with greater than or equal to min over all L PLJ of n minus, or in this case plus, alpha times max over all L PLJ of n minus min over all L PLJ of n. Okay, this is what I get. Okay, so now basically I have this upper and lower bounds on Pij n plus 1. Okay, so now combining the two, okay, so what is it that we will get? We will get, so suppose let's say if you look at for example max over all I Pij of n plus 1 minus minimum over all j or all L P, okay, I'll just use L on all the sides, PLJ of n plus 1. This is less than or equal to. So what will happen? So what I'm doing is, see, I have a lower bound on this. This is true for every I. So what I can do is I can take the minimum of this. Okay. So, and similarly, the other one will be maximum. Okay. So, and subtract the two. So I'll get this. So this and the other term will cancel and you have max over all L PLJ of n minus min over all L PLJ of n times 1 minus 2 alpha. Okay. So now if you iterate, right? So for example, if you iterate this, this will be less than or equal to this with n minus 1 here, 1 minus 2 alpha whole square. If you keep on doing that, you'll get 1 minus 2 alpha over n. This is what you get, right? So in other words, this will be n plus 1 because we have n plus 1. So essentially, as n goes to infinity, 1 minus 2 alpha goes to 0. This goes to 0 as n goes to infinity. Since alpha is sufficiently small, right? I mean, meaning 1 minus 2 alpha should be less than or equal to 1. Okay. Then less than or equal to what? 2 alpha. So 1 should be greater than 2 alpha. Alpha should be less than half. Okay. So of course, alpha to be less than half. Okay. Is that fine? Is that fine? So what does that mean? This implies limit n tending to infinity max over all L P L J of n equal to limit n tending to infinity min L P L J of n. Okay. This is definitely greater than or equal to alpha. Okay, because why is that? Because minimum overall ij pij of n is alpha. That's the definition. So this should be greater than or equal to alpha for every n, and therefore in the limit also it's true. Okay, I think I think we need see here I need this is greater than or equal to n provided the pij n is that's true for every n. So that means where did I define this? This thing. It's Pij. So if you take Pij power n, obviously that's smaller, right? Ij. Okay. Is this fine, everyone? Hello.
Yes, sir. Yeah.
Okay. So now essentially we have proved that the rows of the P matrix, right, goes to a constant vector as n goes to infinity. If you look at P power n. Now the next step is to show that that row corresponds to pi. So in other words, if I take that row multiply by P, pi P equal to pi. That's what we get. That's the that sort of concludes. We should see under what condition that happens. So we will see under what condition you'll get such a pi. And the next question would be under what condition this will be unique. Okay. Fine. Is that
Yes.
fine? Okay, that's the big picture. So once we are done with that, we can look at what is known as Markov decision process. Okay, that's something interesting. We will look into it. Okay, I'll stop here. If there are no questions, then we will end. Any questions?
No, sir.
Okay.